Good morning, afternoon, or evening, everybody. Welcome to the Discover NASA Ocean Color Data and Services at the Ocean Biology Distributed Active Archive Center, or OB.DAAC. This is your host, Jennifer Brennan. While everybody is logging in, most of you have noticed these already. We have two optional polls at the bottom left and middle portion of your page, and I'd like to thank you in advance for your feedback on these polls. I've got 2 p.m. Eastern Daylight Savings Time, so we are going to go ahead and get started here. First, what I'll do is I'll go over a few logistics related to this webinar. To ensure best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is to enter those into the Q&A pod located on the lower right-hand side of your screen. And again, this does work like a chat. This webinar is being recorded. It will be posted both to our online Adobe Connect webinar catalog as well as to our NASA Earth Data YouTube channel within a couple of days of completion. And I'll send the links out to all of the registrants and participants. All presentation files will also be available for download at the end of the webinar. Let's speak really quickly here to the timing. The webinar is 1 hour long. We've allocated 45 minutes to the presentation and live demonstration, with an additional 15 minutes for the question and answer period. After our speaker has finished his presentation, we will then move to a final set of polling questions. I generally will give those 3 or 4 minutes or so. From there, we'll transition directly to the Q&A period. Again, you will have an opportunity to ask your questions throughout all portions of the webinar, with the exception of the live demonstration by using the Q&A pod. It works like a chat. Questions will not be answered today using the raising hand function. It has been disabled. And then one final note for everybody. Depending upon the volume of questions that we receive, we will extend the Q&A period an additional 15 minutes to 3:15 p.m. for those of you who may wish to stay on the line. What I'd like to do now is let's move next to our agenda. I will pull that up for everybody. All right. During the first 15 minutes or so, our speaker will provide an overview for today's presentation and an introduction to ocean color science. During this segment, he will highlight some of the data products available at the OB.DAAC. The second half of today's webinar will be spent with a short live demonstration and a discussion of the data discovery and access options at OB.DAAC. With that, it is my pleasure to introduce today's speaker, Robert Lossing, who is a biological oceanographer and also a scientific software engineer at OB.DAAC. Robert?
Hello, I'm Robert. Let's start the presentation. Okay. Welcome. Today I'll be introducing you to the Ocean Color Data Analysis and Services accessible at the Ocean Color Web. I'll be covering the brief basics of ocean color satellite remote sensing science and a few of our commonly used ocean color products. Then I'll be covering how to access and download satellite remote sensing data and imagery from the Ocean Color Web. I'll also show you a very quick live demonstration of how to do this. And then finally, I'll present some of the capabilities of our powerful free open source image analysis software called SeaDAS. I've created this presentation to be an excellent reference for you to return to later. This page is one of the most important slides in this presentation, and it has links to all the different sections and slides in this presentation. Also, on every slide in this presentation, when you go back, you can click on the upper left-hand corner logo to return to this overview page and table of contents. Just make sure you open it in a PDF reader, and these links should work. I've split this presentation and document into 3 distinct sections that I spoke about earlier. The Ocean Color Distributed Active Archive Center, OB.DAAC, where I will discuss the satellite remote sensing missions that OBPG, the Ocean Biology Processing Group, supports, the basics of satellite remote sensing ocean color science, and the general data products that we produce. The second section, I'll talk about ocean color web data access. In this section, I'll show you our data access browsers as well as additional data access options that we make available to our users. I'll also introduce you to our in situ field database archive called SeaBASS, as well as a new upcoming tool called Giovanni that we're bringing online here at the Ocean Color Web. And at the end, I'll show you a live demonstration of the browsers. Finally, in the third section of this presentation, I will cover the features and capabilities of our image analysis program called SeaDAS. The Ocean Color Web, along with all the data, services, and programs, is supported by the Ocean Biology Processing Group. I call it the OB.DAAC. And we're at NASA Goddard Space Flight Center in Greenbelt, Maryland. We're responsible for the collection, processing, calibration, validation, archive, and distribution of ocean data products from a large number of satellite remote sensing missions. Our primary data products cover ocean color, optical oceanography, sea surface temperature, and sea surface salinity. And the Ocean Color Web also features in situ field data taken from buoys, research ships, field cruises, moorings, and things like that. We've been providing this data free to the research community since 1996, and we possess nearly 20 years of continuous ocean color satellite remote sensing measurements. We have 40 years of data total. At the bottom of this page, you'll see three very important links. The first is our homepage, and then the second is where you want to go to register to download data. It seems like you've all been here before and downloaded data, but now we're requiring our users to register. And then finally, if you have questions, I recommend going to our Ocean Color forum, where there are a lot of frequently answered questions and a lot of engagement with the Ocean Color community as well as the OB.DAAC. Next, I'm going to talk about sort of the satellite missions that the Ocean Biology Processing Group supports. At the OB.DAAC, we handle a variety of missions from over a dozen satellite and airborne remote sensing missions. And I've listed a few here on the right. The links on this page actually go to our respective mission pages for these spacecraft and sensors. In this picture, we are seeing the ground track in red and the swath or image taken during a single overpass of the Indian Ocean by, this is the MODIS Aqua satellite. Many passes occur in a 24-hour time span with data collected from every pass. Ocean color imagery is taken only on the day side where sunlight is required to illuminate the ocean. Sea surface temperature and sea surface salinity can be collected on the night side because sunlight is not necessary. On board the orbiting satellite is a very sophisticated camera called a radiometer. Ocean color radiometry is the study of the interaction between the visible electromagnetic radiation or photons coming from the sun and interacting with the aquatic environment and the constituents within the aquatic environment. These measurements can be used for important information such as phytoplankton algal biomass, photosynthetic microorganisms, or the concentration of other in-water constituents such as sediments or dead leaves that modify the characteristics of incoming radiation. All these swaths from the satellite combine to give us a global image, which I'll get to shortly. The most important light-absorbing substance in the ocean is chlorophyll, which phytoplankton use to produce carbon biomass by photosynthesis. Due to this green photopigment, chlorophyll, phytoplankton preferentially absorb the red and blue portions of the light spectrum and reflect green light back. Ocean regions with high concentrations of phytoplankton will have shades of blue and green depending upon the type and density of the phytoplankton population there. So essentially the most basic principle behind this is that ocean color, the more phytoplankton there is in the water, the greener it is. But remember that we have ultra-sophisticated cameras on orbit, and we can see more than just red, green, and blue. At the bottom of this page is a link to our image gallery that has a lot of these images if you're interested. This chart shows the various wavelengths collected on orbit by our ocean color sensors. These come from past, present, and potential future satellite remote sensing ocean color missions. Ocean Color is primarily interested in wavelengths covering the visible spectrum, which is 400 to 700 nanometers, with some measurements covering the ultraviolet to near infrared. We use those wavelengths for atmospheric and aerosol retrieval measurements, which we use to remove the atmospheric signals in order to see ocean color more clearly. We call that atmospheric correction. Current ocean color missions are limited to a few wavelengths, however, called multispectral missions, and these allow us to differentiate between a few environmental substances. At the moment, we can see the marine algal phytoplankton in the ocean and can estimate the quantity of phytoplankton biomass. An analogy would be that we're seeing the whole forest or pasture of marine phytoplankton populations. Proposed future sensors may be hyperspectral in nature, which will allow us to differentiate between algal groups and measure the physiological states of algal blooms, with the analogy that we may essentially start seeing the various spectral signatures of the different trees or begin differentiating between apples and oranges of phytoplankton functional types. This will help us understand more about the quantitative health and functionality of phytoplankton ecosystems. So once again, with the various wavelengths captured from the satellite, we're capable of measuring the concentrations of marine phytoplankton using their photosynthetic pigment chlorophyll A. This is a map of chlorophyll A on the eastern seaboard in the Atlantic. As the concentration of phytoplankton increases in the water, the color of the water shifts towards the green part of the spectrum, and we're able to capture that from orbit. Monitoring the spatial and temporal variability of algae from satellites allows us to have a large coverage of oceanic basins and regions, and it's been instrumental in characterizing the variability of the largest ecosystem on Earth. This global ocean color radiometry is a critical tool for researchers looking into how these global marine ecosystems respond to hydrological cycles, climate shifts, as well as human impacts. NASA satellites also measure the temperature of the ocean surface. These measurements are valuable for studying marine phytoplankton ecosystems because phytoplankton growth depends upon the availability of sunlight, temperature, and nutrient levels. Since cold waters tend to be contain more nutrients than warm waters, phytoplankton tend to be more plentiful where waters are cold. In this map, we can see the coldest waters appear in violet and blue, while the warmest temperatures appear in red and orange. Notice how when I transition between this slide and the previous slide, you can see how the phytoplankton populations are found in the colder regions. So now you're starting to get the hang of ocean color remote sensing. Now we're looking at a chlorophyll A map photopigment for the entire planet Earth. Just look at all this phytoplankton, billions and billions of tons. I want to now quickly go through the various commonly used products produced by the OBPG and made available online via the Ocean Color web. I'll try to give a brief description of each product as well. When we're going through these maps, try to imagine the complexities of interactions occurring in the ocean and how we're able to measure them from space using satellites. Normalized fluorescent line height, NFLH, provides a measurement of the efficiency of photosynthesis. High fluorescence is typically found in low iron waters, while low fluorescence dominates regions where other environmental factors are most limiting to phytoplankton growth. Specific properties of photosynthetic membranes may be linked to iron stress as well as fluorescent detection. Satellite fluorescence may also provide a path for monitoring climate, phytoplankton physiological interactions, as well as improving descriptions of phytoplankton light use efficiencies and ocean primary productivity models that we talked about later. Sea surface temperature is another valuable variable that we make available. It is the water temperature close to the ocean surface at about 1 millimeters depth. In places where ocean currents cause upwelling, sea surface temperatures are often cooler than nearby waters, and chlorophyll concentrations are higher, like discussed earlier. This connection is evident in multiple places. A band of cool phytoplankton-rich waters circles the globe at the equator, with the strongest signal in the Atlantic Ocean and the open ocean waters of the Pacific. In many coastal areas, the rising slope of the sea floor pushes cold water from the lowest layers of the ocean to the surface. These rising upwelling currents bring iron and other nutrients, causing blooms, which are most evident along the west coast of North and South America, as well as southern Africa. Photosynthetically available radiation is another variable that's powerful for our users. It designates the spectral range of solar radiation from 400 to 700 nanometers that photosynthetic organisms are able to use in the process of photosynthesis. Phytoplankton require just the right quantity and quality of light to be most productive. Too little or too much light and their productivity plummets. The subtropics generally have the highest PAR values due to persistent, intense year-round sunlight, while the lowest PAR values are seen as you approach the poles at high latitudes. And keep in mind that the Earth's seasonality also causes large shifts of these measurements over the year. Spectral backscattering is a measurement of the particles in the water. It is an especially powerful measurement in conjunction with other satellite data products and can be used to differentiate between living and non-living particles such as sediments versus phytoplankton, etc. Aerosol optical thickness. Aerosols are small particles in the atmosphere that can be smoke from forest fires, sea surface, salt spray, dust from deserts or mountainous regions, pollution or volcanic ash, etc. Depending on their size and type and location, aerosols can either cool or warm the surface of the Earth. They can also help form clouds, or they can inhibit cloud formation. And if inhaled, some aerosols are harmful to public human health. At the Ocean Biology Processing Group, we're most interested in the aerosol optical thickness in order to remove it, in order to get clear measurements of ocean color data. Another variable that we make available is the diffuse attenuation coefficient. This algorithm returns the downwelling irradiance at 490 nanometers. The diffuse attenuation coefficient in water indicates how strongly light intensity at a specific wavelength is attenuated or diminished within the water column. This parameter has wide applicability in ocean optics and is directly related to the presence of scattering particles in the water column, either organic or inorganic, and thus is an indication of water clarity and turbidity. And finally, one of the last commonly used products that I'm going to talk about is sea surface salinity. While sea surface temperatures and ocean color have been measured for the past 30 years, we've only recently been able to measure sea surface salinity. And keep in mind that ocean color and sea surface temperature measurements are taken at about 1 kilometer resolution. Sea surface salinity is on the order of 100 kilometers, so the resolution is nowhere near what we can get with ocean color and sea surface temperature. Sea surface salinity and sea surface temperature measurements are used to calculate the surface density of the ocean. And surface density in turn drives ocean circulation and currents. Understanding ocean circulation is critical because it's it's important to understand the transfer and of heat over the Earth because the oceans have 1,000 times the heat capacity of the atmosphere and thus have a dominant effect on global hydrological cycles, climate change, and marine ecosystem variations. One second. Okay. While impressive research data sets in their own right, these Ocean Biology Processing Group produce products like chlorophyll A, sea surface temperature, and PAR. They're also critical inputs for other products, and one of those is calculating primary productivity. I'd like to note that while the OB.DAAC does not produce maps of primary productivity, our data is used by Oregon State University to produce them with the link provided. Now that I've quickly shown you a few of our products, I'm going to move into the second section of this presentation where I'm going to describe the satellite remote sensing levels and file naming formats. At the Ocean Biology Processing Group, we are constantly working to give researchers the best quality data as well as make it accessible as possible. The Ocean Color Web serves this purpose by providing you all the tools and browse options to download data as well as services and programs to empower your research. This page is a brief summary and reference with helpful links to our website's user registration page, data browsers, etc. Next, I'll summarize our many products and temporal aggregation options. So once again, we make available a huge variety of products covering biological oceanography, algal pigments, ocean optics, biogeochemical estimation, sea surface temperature, sea surface salinity, algal functional types. We also make available all the various wavelength measurements used to calculate radiance and remote sensing reflectance that determine these geophysical parameters. You should click on the link at the bottom if you'd like to read more about the algorithms used to generate these products. And keep in mind that we aggregate or composite our data to create products that cover that day, which we call a daily. We create 3-day products, which are 3 days averaged together, going up to 8 days, monthlies, yearly composites, seasonal composites, as well as climatologies. Like a monthly climatology would be all the Januaries averaged together. These are getting into what we call level 3 satellite data, which I'll talk about the levels of satellite data next. So satellite remote sensing data can be ordered into 3 major levels of data processing. This is a very common concept across all remote sensing disciplines. These processing levels describe the level of computer processing required to refine the data. Data levels 0 through 1 are mainly used by us in-house at NASA. You'll primarily be interested in using levels 2 and level 3 data, which I've colored green. As you increase the levels of data, you're increasing the data processing. These are the arrows on the right side. You're increasing the general usefulness of the data, and you're increasing the data refinement, and you also happen to be increasing the uncertainty and decreasing the confidence of the data. Because as we apply more and more algorithms, we involve more and more uncertainty to the data. Level 2 data is comprised of individual satellite scenes or granules that are subsets of the entire satellite swath that I talked about earlier. And we've subset the swath to make the processing easier for us and for you. Level 3 data is comprised of all the granules composited or aggregated together, usually for a month, day, year, etc. These are the global maps that I was showing you earlier of the commonly used products. And I just want to note that level 3 has 2 subtypes, bin versus mapped. Bin level 3 data is used for statistical analysis, while mapped level 3 data is primarily used for imagery. Next, I'll be showing you how these data processing levels show up in the file names when you're eventually downloading an image or granule. When downloading data from us, it's important to understand the file name format because it provides a quick way to differentiate between the file as well as provides a simple description of the file. These names contain the sensor IDs, time and date when it was imaged, levels of processing as well as products included in that file. These names are also unique identifiers for that individual satellite image. All of our files end in the .nc extension, which means that they're a netcdf data format. And later I'll talk about our SeaDAS program, which can read all of these files. I'll discuss this in the final section of this presentation. And once again, at the bottom, or excuse me, at the top, the blue format documentation link provides more detail on this topic. Next, I'm going to show you our first data browser. This browser is specifically used for downloading level 1 and 2 data from our supported missions. This is a screenshot of the web page where you search for and select levels 1 and 2 data to download. Remember that levels 1 and 2 data is comprised of the individual granules that make up a single satellite swath or overpass. Provided links at the bottom corner where you can visit this data browser as well as visit the help pages. And I'll be showing a live demonstration of our level 1, 2, and level 3 browsers shortly after I've shown you the few screenshots of them. These browsers are fairly straightforward to use and very capable of allowing you to discover data in a various variety of ways. Simply clicking anywhere on the map in the location will likely return a very long list of files that fall under that clicked location. Currently, looking for the arrow. Currently, we're looking at a complete mission composite of the SeaWIS Aqua mission. And if I click here in the middle of the Atlantic Ocean, it'll return me a whole bunch of files that fall within that pixel region. So these are the search results for that clicked region. All satellite images for the chosen sensor that had that pixel location were returned. I've added a red square at the bottom right-hand corner in this presentation to highlight the approximate clicked location. You can see the file names at the top of each respective browse image in blue up here. Clicking on the file name will download the file. You can also click on the actual browse image itself to get more information on that file to download. And I'll show you what that screen looks like later. Some users may want to download a lot of images and granules, so you can use the cyan order data button to bulk order data. In the next slide, I will show you how we can return, we're going to return to the previous slide, and we're going to search for ocean color data taken October 10, March 2010 by the MODIS instrument aboard the Aqua satellite. So you'll see the global map change from the current complete mission composite shown here to just the overflight. This is the overflight for that single day. So see how the complete mission composite map is gone, and now only the swaths, overpasses that occurred on my search data are present. I can now click on the red square rectangles or granules to view that individual image or scene. So I'm going to click on one, click. Now we're looking at the individual characteristics of a single level 2 image or granule or scene. And we have various options to download, which I've highlighted in the upper left-hand corner with red brackets. Remember that we have various categories of products: ocean color, inherent optical properties, sea surface temperature when available, and we also offer the level 0 and level 1, which you can see in the file names here. Those are much larger files because they have a lot more data in them than the sort of stripped down single product versions. And please use the helpful links at the bottom left. Next, we're going to look at the level 3 data files and data browser. This will show I'll show a global composite image that the Ocean Biology Processing Group makes, and we can provide all of those on the Ocean Color web to you. Level 3 data is comprised of collecting all the level 2 granules for that day, week, or month, year, season, and compositing them together to form a global image. The OB.DAAC has done this processing for you, and these files are available via the Ocean Color Web Level 3 browser, and the links that discuss this compositing and processing are discussed down at the bottom under the binning documentation. Next, I'll show you a typical level 3 image that we create. So this is like the Chlorophyll A that I showed you in the past. So we make these available in a variety of different temporal compositions. Now we're looking at the level 3 browser. This browser is extremely straightforward. Once again, I've provided links in the bottom left corner. I'm just going to talk about a few highlights of this browser. Here we can see the various options for downloading level 3 satellite files. At the top, we have drop-down bars, which are used for selecting the missions and products, the timescales, the resolutions, and as well as the product class and how many you want to show in a single screen. Picking a date for data is as easy as picking a date among the calendar months at the bottom down here. And then you click on your image here, or hover over it, excuse me, and there are 3 formats that you can use to download level 3 files. The first one is you can click on the image and you'll get a PNG file. The second one is you can click on the SMI HDF and you'll get a standard mapped image file. And then the third format is a binned HDF file. So this is our additional data access options page. We have links provided to each of these data access tools. Direct data access is if you like the file cabinet search option. Everything is there, but you have to go search through the folders for it. Data file search lets you search for a file if you know the file name. And data subscription lets you set up a subscription to get new granules over your research location whenever a satellite passes over that and collects data. OB.DAAC is for super users who want to set up map servers such as NASA's Worldview. So now I think we can switch to a brief live demonstration of our website and data browsers. So if you can all see this, I've gone to our website. I'm just going to show the first level 1 and 2 browser. So you go up here to data, click on it, and here we're seeing the complete mission composite like I showed earlier. So I can click anywhere on the map. I'll look at this South Pacific gyre here, and I've got a collection of hundreds of thousands of images showing up within that single click region. I can also search for a date, March 12, and I can find, these are all the granules that were taken that day, and I can click on one of those to get more information on that image, and I can download them up here. Now I'm going to go to the level 3 browser, which is here. And this one's very easy to use as well. I can pick from this drop-down menu a tremendous amount of products from many of our missions. So I can do chlorophyll concentration, and I want and an annual composite. So this is an annual composite of 2001, and I can see it here. So it's pretty much that easy to download stuff. Here are the two other options to download data. And at that, I think we'll go back to the presentation.
Okay.
Okay. So in addition to satellite data, the Ocean Biology Processing Group also maintains a database archive of in situ field data. We use this data to ensure that users are getting data from the highest, with the highest quality. This archive we call SeaBASS. In this database are pigment concentrations, inherent optical properties, apparent optical properties, water temperature, salinity, stimulated fluorescence, carbon stocks, hydrography, and other biogeochemical and atmospheric measurements. In the next slide, I'll discuss how these measurements are collected. And there's a link at the bottom to this search browser for the in situ data. These measurements are primarily collected from research ships, moorings, buoys, field radiometers, and we have almost 80,000 data files from over 2,500 field campaigns, collected by over 130 investigators from more than 85 U.S. and international institutions. The map in the middle shows all the data points that we've collected. And the purpose of this, any NASA ocean biology and biogeochemistry research crews in which field measurements are collected will be archived there. These in situ measurements are extremely useful and used to validate ocean color satellite measurements, develop satellite algorithms, calibrate instruments, as well as correlate satellite data with actual environmental data. And for the last part of this section, I'll just discuss our new tool coming up, which is Giovanni. Giovanni is a web-based application developed by Goddard Earth Sciences Data and Information Services Center, GESDISC. It provides a simple and intuitive way to visualize, analyze, and access vast amounts of Earth science remote sensing data from many different disciplines without having to download the data. At the Ocean Color Web, we will be making available an instance of Giovanni that will feature additional data sets specific to the ocean biology and ocean optics fields. Lots of middle school and high school educational classes are taught using Giovanni, since it's a very simple program to use and requires little prior remote sensing experience. While Giovanni has numerous statistical analysis capabilities shown here, you can do rapid research investigations with it with earth science data, but if you want to do more dedicated analysis, you'll want a more powerful platform for handling ocean color imagery and data in order to provide the best possible use of the data. This sort of concludes the second section of downloading data at the OBPG's Ocean Color Web. In the last section, I'll just briefly go through our SeaDAS image analysis program, which will allow you to investigate ocean color imagery, do powerful statistical studies, and produce amazing research publication figures. So finally, we've made it to our SeaDAS image analysis program. I hope by the end of this section, you'll be very interested and confident in getting data started and used in SeaDAS. You'll be able to view and study your downloaded ocean color imagery data like you've never seen it before. So this page is a very helpful resource for all the links which are associated with SeaDAS. Okay, I'm missing some of my notes. So SeaDAS, we're currently at version 7.4. There's download links here provided. We have a very huge amount of missions supported, not just ocean color missions, but missions like Landsat, ESA's, ULCHI. We provide a link down at the bottom for tutorials and frequently asked questions, as well as the source code is open source. So SeaDAS is pretty powerful. I'm going to show the interface here. And I'm going to quickly go through some of the options, capabilities of SeaDAS. I'm sorry I don't have a summary of them at the moment, but we'll get through them pretty quickly. So like any image analysis software for remote sensing, you're going to want to do projection and reprojection of imagery. These are just a couple examples here of common projections for satellite imagery. And SeaDAS is like any other image analysis program. We can do projection. So here we're projecting an unprojected level 2 file to 3 other different projections. So it can be done. If you've used Landsat remote sensing in the past, you'll be very familiar with the different band combinations of imagery. You can use different wavelengths to look at red, green, and blue for sort of a true color image, or you can pull out and distinguish features from vegetation and soil, ice, snow, and clouds using the different wavelength combinations. And SeaDAS is able to do that as well. So using, we have something called a math band, which will allow you to create your own algorithm. So this is an algorithm that's an optical apparent depth, and they're using the KD490, which I talked about in the beginning of the presentation, to get sort of a water clarity or light extinction coefficient in the marine subsurface. SeaDAS, you can merge level 2 files to create sort of a level 3 global composite. So the image in the upper right-hand corner here, this image was created using 500 level 2 files, and you can create a global image that way. We've done all the processing to do level 3 products for you, so you actually don't have to do this at all. You can download level 3 files from the Ocean Color Web Level 3 browser. So masking is a powerful tool to select and highlight data. Because SeaDAS is specifically targeted to using ocean color data, we want to make sure that you are using the highest quality data in your research publication or investigation. So we've made it utilize the quality control flags that tell you where we're uncertain of the quality of that pixel or the data return there. So you can turn these flags on, and you can see where there might be high sun glint, where we believe the data is unusable, as well as we can't return ocean color data below clouds or over thick aerosol regions. Or if it's under ice, we can't return ocean color data there. You can use these masks to do other sort of selection of imagery. Here we're using a bathymetry mask that's used to select chlorophyll, as well as exclude it from a bathymetry area. SeaDAS also has very powerful and extensive color palette capabilities and a multitude of options and choices. You can have colorblind compliant palettes, or sort of a more natural color palette for your product. The color palettes can also be used to highlight features in various low and high regions to make them stand out. So here you can see low chlorophyll. We've changed it and stretched it so you can pull out features, as well as in high chlorophyll regions, we're pulling out more features by changing the color palette. This program is extremely powerful. You can do a whole bunch of statistical capabilities with it. Won't go into too much detail here, but just to say that we've made it as accessible and easy to use as possible. In SeaDAS, you can also do trending data over time. You can do time series analysis to study ocean seasonal cycles, which is extremely useful for those wishing to study ecosystem fluxes or sediment fluxes down rivers and things like that. A very powerful tool that is available in SeaDAS is the pixel extraction tool, and that lets you use field measurements to select satellite data matchups for pixels and things. And we make every effort to make SeaDAS data outputs as accessible and available to use in a wide variety of other analysis programs, as well as data science programming languages. Next, I'm going to show I'm going to quickly show you 3 case studies which highlight all these capabilities put together. I hope you really help. I hope these help you understand and are interested in working with SeaDAS and start to get your mind thinking about your own possible investigations using our data, services, and tools. So in case study 1, we're comparing satellite imagery from 2 sea surface temperature measurements. So we have a nighttime sea surface temperature and a daytime, and we can do a correlative percent difference maps as well as scatter plots. In this one, we're showing comparing different satellites with SeaDAS. So we have a Modus Aqua sensor as well as a sensor board called SeaWIS. And we can do percent differences and scatter plots between different sensors and spacecraft. And the third case study I'm showing is, this is a field cruise that went out and was sampling regions off the coast, the east coast of the eastern seaboard. And over the course of this week-long cruise, we had a few different satellite swaths that overlap with the cruise, and we used the pixel extraction tool to show off places where we had matchups with the satellite and the samples that were taken by the research crews. And we've created a correlative plot here. So you can do a lot of fantastic publication quality images within SeaDAS. And I wanted to show you that we have a tremendous amount of tutorials online on YouTube, as well as our own training pages, and there are links provided on this page. And then if you have any questions, come to the Ocean Biology Processing Group's Ocean Color Forum and ask them there. There's a huge community present there, and they're always helping each other out. And we also make it a habit to participate in those discussions. So thank you. That's all I have. I'll turn it over to Jennifer. There are links provided at the bottom to the forum as well as to the website.
Okay, great. Thank you, Robert. Thanks, everybody. What we're going to do now, and we are just a couple minutes behind schedule here, but we'll take a few minutes. Let's give these end polling questions about 3 minutes or so. And for those of you who are able to stay on the line, if you have additional thoughts during the Q&A period, feel free to enter those into the Q&A pod. And from here, we'll move directly to the Q&A period. We'll extend that Q&A an additional 15 minutes for those of you who do not have a hard cutoff at 3 o'clock. All right, so we're going to give this just a couple, and then we'll move forward. Everybody? Okay, everybody, we're going to give this about another minute or so, and I've noticed there have been a couple of questions about OB.DAAC and threads, and for those participants who are interested in that kind of information, there have been several webinars that have been held that incorporate, kind of a step-by-step demo using threads and OB.DAAC. And I can email you offline with some links to webinars and kind of point you to where you need to go within the webinar to see some examples. But certainly this is excellent feedback for developing future tutorials. So thank you so much for taking the time to really think about these questions. All right, everybody. We're going to give it about 30 more seconds.
Hello, this is Robert. I just want to say that I really appreciate all the responses coming in, and this is a huge help for us because we're continuously trying to improve our data as well as improve the access that you guys have with handling it. So I really appreciate that. Thank you very much.
Great. Thanks, Robert. At this point, everybody, we are going to move to the Q&A period. But if you think about feedback that you would like forwarded along to Robert, feel free to email me or, again, type it into the Q&A pod. So let's get started here since we're a little bit behind schedule. The first question that we had to do with one of the users was asking about primary productivity estimate data. If you could speak to whether or not, that's available,
Yes.
Okay, great. Thank you.
So the Ocean Biology Process Group does not have its own primary productivity data, but our data is used by Oregon State University, and they have a primary productivity website where you can get maps of primary productivity. And in this presentation, there is a link to that to their primary productivity website.
Okay, wonderful. Thank you, Robert. The next question is, can you explain more about the different resolution types, LAC?
I'll do the best I can. So LAC, I think it's local area coverage, which is usually in terms for the SeaBASS mission has LAC and GAC. So LAC is where the actual satellite had a direct downlink communication to a satellite receiver. So it can have a much higher resolution than the global area coverage, which means the satellite had to store data on board the spacecraft until it could downlink the data. So GAC is actually a lower resolution because due to the hard drive space available, you had to cut out something like every fourth line had to be removed for GAC. But LAC, local area coverage, was a direct transmission downlink, and you could send down the data as fast as you could image it. So it didn't have to be stored.
Okay, great. Thank you, Robert. The next question I did answer within the Q&A pod. One of the users was asking whether or not there are similar terrestrial products available for download, such as NDVI, carbon stocks, biomass. And the answer to that question is yes. There are two NASA DACs that have data products related to what you've asked, and I will email you offline. The first is our Land Processes DAC in Sioux Falls, South Dakota. They have NDVI among many other, phenology and other data products. And related to the carbon stock and biomass types of data products, there are a number of regional and global data products available that cover, the North American Carbon, NACP program data products, some very specific regional carbon stock types of data products at Oak Ridge DAC. So I will email you separately with additional information. And then our next question is, needing a few more words about the use of OB.DAAC for your data products, for access to your data products.
Yeah, we are just trying to support our OB.DAAC, so I'll have to get back to you on that one. We're putting in place a new server to host OceanDAAC data. Our first use of it has been with getting the Giovanni set up, so that's coming very shortly. And I'm hoping eventually we might do some new browsers that are running off OB.DAAC eventually. So come back and look for us in the future, and we might have some neat things to show you on OB.DAAC. But if you have any specific questions on OB.DAAC, please let Jennifer know, and I'll try to get you a response, offline over email. Thanks.
Okay, great. The next question is, can you elaborate on a slide footnote saying something like, MODIS on Terra does not yet provide science quality ocean data. Does this mean there are data at ocean data sci gsfc.nasa.gov that should not be used?
The MODIS Terra instrument had a anomaly that happened, so the quality of that data is not scientific quality data. Compared to the MODIS Aqua instrument is highly calibrated and validated. So any data that comes from the MODIS Terra instrument is cross-calibrated to the Aqua instrument. So you're seeing any artifacts that come from the Aqua instrument will show up in Terra instrument because due to the quality of the Terra instrument, it just can't produce the anomaly qualities that occurred, just can't produce the high quality data that MODIS was able to produce.
Okay, thank you, Robert. The next question is there a way to find all the data that were collected simultaneously, like AOPs and IOPs of the same location for the same time?
So that's a SeaBASS question, and I'm not an expert on SeaBASS. I would, if I'm not comfortable answering that, I'll have to forward that to the SeaBASS group, and there should be a email that they can send that to.
Yes,
but
and just to let everybody know, the Q&A log will be sent to Robert, so he will have information that will allow him to follow up offline on all of these questions, okay, if they're not answered during this time period. And speaking of time period, we're now entering the extended 15-minute Q&A portion of the webinar.
Yeah, the SeaBASS data is, I just haven't used that browser too much. I'm more on the imagery data side versus the in situ data side. But I will, I'll get a list of those questions and I will try to answer them individually, and Jennifer can give that back to you.
Absolutely. Okay, so our next question is, can you tell us the history and future of SeaDAS with regard to the transition to using the, actually, Robert, if you would not click on the questions because that will make it harder for me to, I don't know if you are, but.
Okay. I don't think so.
With regard to the transition to using the ESA beam interface, can you tell us the history and future of SeaDAS with regard to the transition to using the ESA beam interface?
So SeaDAS, the heritage of SeaDAS is it comes from ESA's beam, and I believe they have a new interface called Snap. We're developing SeaDAS in parallel, and it's pretty much our own product. So I don't believe the interface of SeaDAS will change that much in the next couple of years. But I know that the beam has gone to a Snap interface, and I'm not familiar with that interface. But I just want to say that currently you can use SeaDAS on Mac, PC, Linux, Unix, but to do some of the processing, it's not available on PCs, but we expect sometime maybe midsummer 2017 we'll have processing, which will use the Ocean Color scientific software that we use to produce this imagery. But that is available on Macs and Linux boxes.
Okay, great. Thanks, Robert. The next question is, are all of the data that are viewable graphically in SeaDAS, histograms, time series at a pixel, etc., exportable as a CSV file?
I believe so, yes. And you can also, those graphs, you have a huge amount of control over the figures that create those graphs, change the legends and axes, etc. And you can save them as PNGs as well. So there's a couple of ways to do that. If you have questions on how to do some of these things in SeaDAS, I highly recommend the video tutorials that we make. They do a great job and are pretty exhaustively covering all the capabilities there, that many which I had to gloss over for the sake of time.
Okay, thanks, Robert. The next question is more of a user need, that this particular user needs more information on how to convert the output format into ArcGIS or QGIS. So I don't know if you have any tutorials available on your YouTube channel addressing this. I know that we do not.
That's something I'll look into. I'm aware, being a remote sensing scientist and user, I've used ArcGIS in the past extensively, but here we primarily use SeaDAS, but we should, and I'm pushing to get our data more accessible on ArcGIS. So I will bring that up and try to, we'll try to get something out there that addresses that. So that's a great question and comment.
So Ed, I'll be sure that, there's some follow-up on this question offline as well. Okay, so the next question is basically more of a combination comment and question. More on Modus Terra. So should we not use these data and use Modus Aqua instead? Also, should Modus Terra not be used for Modus land products? I can't give you an answer on the land products, but you absolutely should use Modus Aqua instead of Modus Terra. I think there should be somewhere online that'll discuss sort of the engineering problems that happen with the Terra instrument and why it doesn't produce climate quality variable data. And essentially it is calibrated, or it's cross-calibrated to Aqua. So Aqua has a better fidelity and higher, we have a higher confidence in the spectral characteristics of that sensor than we do for the Terra instrument. I believe something, something with the, there was like an over voltage on that sensor that sort of off-gassed onto the optics. So it has sort of a blurrier optics than the Aqua sensor had during the design and construction and testing. Okay, thanks, Robert. And Sarah, I'll follow up offline with you regarding the Modus land data products. There's some specific documentation online, and I can put you in touch with the user services office at the OB.DAAC. You can get the answers that you need on this topic. So
the new sensor is the VIIRS sensor, and as Modus Aqua I guess it's almost approaching 15 years of life, and over that time span, the sensor is degrading, and I think we now say that you should use VIIRS data for ocean color remote sensing. It had some problems in the initial early part of the mission, but we've done our best to calibrate those, and I think we stand by VIIRS data as climate quality variable data. And there are white papers out there that describe that for, as a reference. You can see calibration and validation research activities that we've done also on our website. I didn't show these for the presentation, but we do put up mission trends for the different sensors. So if you're interested in seeing the quality of the data that we're putting out there and how we're calibrating it, we do make that is public. But usually there's such a small subset of people that are interested in that data. It's not, for your introductory presentation.
Okay, thanks, Robert. The next question is, now there are two Copernicus Sentinel satellites allowing a 5-day repeat schedule. What do you think that can add to ocean research?
Well, there is another sensor that's called GO-SEA, and I believe it takes a photo every 30 minutes, sort of a geostationary sensor. So essentially, you want to see ocean color throughout the day, because as the sunlight passes over, you get different PAR values and different nutrient levels throughout the day, and you can see blooms occurring and depleting throughout the day. So ocean color is not like land remote sensing, where you can look at the rainforest or the grasslands and they don't change over a year. Ocean color is extremely variable, and it changes hourly. So the more measurements you can have, the better. I guess that's what I have to say on that.
And I just wanted to add that the Sentinel-1A and Sentinel-1B data, the synthetic aperture radar data, is available through our Alaska Satellite Facility, DAAC, through an agreement with our European partners. So that's something, Walter, to keep in mind. I can email you a little information there. The next question is, hold on one moment, please. OCM. Can you speak to OCM processing and SeaDAS? It's not really formed as a question, so I hope if I'm not stating this correctly for this user, could you elaborate a bit? Thank you.
I'm blanking on the OCM acronym. Just I kind of exhausted after that presentation. So processing in SeaDAS uses the OCSSW software suite. It's the Ocean Color Scientific software, and that uses things like L2Gen, which takes the level 0 and 1 files and calculates using the satellite algorithms to create level 2 files. So that L2Gen has a huge variety of satellites it supports. I cannot recall the OCM. It sounds familiar. I'm just blanking on it at the moment. But that processing code is open source and available. But keep in mind, if you have a PC doing OCSSW processing for imagery, can only be done on Macs and Linux currently. But we expect PC to be available sometime mid-2017.
Okay, thanks, Robert. So I'm scanning the list here. I don't think that I have missed anybody's questions. Are there any additional questions? We've got about 5 minutes left to the Q&A period. And while we're giving this a minute or so to see if anyone has anything further, just to draw your attention to the lower right-hand corner of your screen, you'll see that the presentation is available for download both as a PowerPoint file as well as a PDF. Okay. If you click on either of those two files, you should be prompted to download the file. And this is a persistent feature, so if you access the recording, which I will send the links out to everybody who registered for the webinar and participated as well, of course, you'll still be able to download the presentation files at a later date by simply going to the end of the webinar.
So the OCM is the Ocean Color Monitor. It's an ISRO satellite by the Indians. And I believe we do have processing capability for that because our L2Gen code is pretty capable. But I'll have to check it, and if that is a question that's in the Q&A, I will get a response to that.
Okay, great. Thanks, Robert, because the individual is asking for the link and support for processing OCM.
Okay.
So you can follow up offline with this. We've got about 3 minutes left. If there are no further questions, just a few words. I would like to thank everybody for participating. What we generally do is I will leave the virtual meeting space open for 10 minutes, You're very welcome. For those of you who may wish to, download the files, or you think of something that you didn't ask earlier, but we will log off from the audio component of the webinar. So I'll give this just another minute or so. Anybody have any further questions? And for those of you who might be interested in sea surface temperature products, while the OB.DAAC does have sea surface temperature data products, we also have a number of additional data products with respect to sea surface temperature, more your physical oceanography products at the Physical Oceanography DAAC. So feel free to email me if you have questions on that topic. Are there any further questions?
I'll try to answer the questions in the presenter chat.
Sure. No, you can. Sure, that would be fine. If there are no further questions, what we'll do at this point, let's see. What would be the accuracy of CHL results?
Once again, it depends on the quantity, or the quality control flags for the pixel, but I believe satellite measurements are like 25% accuracy. As like a general rule, 25 to 30% of what, so you can use that to get pretty close. If you go to the SeaBASS website, you can see validation matchups that match in situ samples of chlorophyll to satellite measurements, and you can see directly, some of the matchups of how close the satellite can get to the in situ measurements.
Okay, and that will be our last question for the day. We've reached the end of the webinar. I would like to thank our speaker, Robert Lossing, and thank all of you for participating today. And we can try to address any of the further questions, in the Q&A pod for the next 10 minutes.
One of the questions, is it underestimate? I think that's sort of around the number, I believe. I'll get you a more precise, referenced answer for that.
Okay, great. All right, I'd like to thank everybody. If you go to tinyurl.com or data webinar, you will see a place to sign up to receive future announcements. We will feature a different earth science discipline every month. And you can sign up to receive announcements, and you can check out all of our past webinars and see whether or not there might be something on the topic you are interested in by going to the YouTube channel. All right, well, thanks, everybody. At this point, we will log off from the audio component and leave the virtual meeting space open. All right, bye-bye now. Thanks, everybody.
Thank you very much.